Um, so I really want you to understand my end goal. So my end goal is not train you how to compute. Of course, I mean, if I put that way, it's kind of wrong. So I want to train you how to think. Okay. So what I mean by think. So I want you to be able to answer this kind of question, whether or not you know the material. What do I mean by that? So if suppose that you ask a question to any person, how do I get to soul? Right? So this is an example of explaining what I think about what you want, what I expect you to be. So say you ask some person, how do I get to the soul? And if you want the answer, the assumption is that you know what the soul is, right? If I ask a question about the inner product size and direction, you need to understand what this inner product size and direction means. Otherwise, unless I give the full answer, concrete and complete answer, you're not gonna get it. You're not gonna understand the answer. So what I mean by I want you to be able to think is that whenever you are asked a question, then you should be able to figure out what you're looking for, what you're trying to get out of it, so that if you see someone's answer or someone's explanation, so that you can agree or disagree with that answer. Okay? So you're not just accepting facts, you're accepting an idea. That's what I mean by when you are thinking. So inner product, so we want to define an inner product, right? So what is inner product? What is the substance of inner product? So inner product is something that you can get as a number, right? It's a number. First of all, you have to think that inner product is a number, but it's not random number. You only get a number, that number, when you have two vector. And it's not just random two vector. That vector has to be the same dimension. That's why I gave you the condition here. It's an inner product between two n-dimensional vectors. So if you really want to explain about the inner product, you have to understand what the vector is and what the dimension of vector is. So anyone can share your idea or group idea about the first question. Anyone willing to share your idea? Two dimension, okay. Okay, so you gave the formula. So you want, so you take to explain what the inner product between two-dimensional vector is, you take two vectors called A and B, right? So and then A is A1, A2, B is B1 and B2, and the inner product is denoted by AB. It's A1, B1 plus A2, B2, and I'm omitting all the sentence. But this is basically the essence of your answer, right? Anyone else have other ideas about inner product? Yes. What was your answer? Yes. Oh, you wrote that in a word. So instead of writing in a symbol, you wrote that in the sentence. Okay, so he said, okay, so I made it as a sentence that it's the sum of element-wise multiplication. Yes. And the reason why we have formula like this is to eliminate all the confusion when we put it in words. So element-wise sometimes means that, okay, can I mix the order of the elements? And people may confuse about in what order should I take a multiplication? Can I take 3 out of each of these and then take multiplication? And maybe that might confuse someone. So the formula is to make it clear. But however, there's no answer. So either you put it in sentence or formula, you're delivering the idea, okay? So is it wrong when I put instead of A, if I put V, is it wrong? No. So what am I looking here? We are looking for the idea, right? As long as you can deliver the correct idea, then everything is right. But you have to have the same idea, right? Right? That's the point. So I want to dig up your thinking. So you might just memorize the formula of inner product, but I want to dig it more. I want you to dig it more so that what you're thinking about the formula is this, and I want to find out the essence of that formula, essence of the definitions, and then I want to be able to write that in your own language, in your own way. So if you want the formula, then you can write in formula. If you prefer write it in sentence, you can write it in sentence. So that's the real understanding. Okay? So if you just simply memorize, it doesn't get you. Okay, so 3-dimensional, we can skip that. So how about the second part? Explain how the inner product determines the size and direction. So size is clear. How can anyone explain about the size? Yes.
So we just need to explain the formula and what's this?
Yeah, you can explain the formula, or you can write say in sentence, whichever you want. What's the size then?
The size is a product of the square of the rise and the run of the each vector under the square root.
Okay, so size, let's say we denote it as this, and it's the square root of, is that the multiplication of each entries?
Yes, square of rise and run, and we need to find the sum of them, and then write it under the square root.
Okay, so let's say V is 2 dimensions. So V1, V2 is the entry. So V1 square plus V2 square. And that's the size you mentioned.
Yes.
Okay, so yes, if you have a formula, it's clear. So how about the direction now? So I didn't say you have to define the direction. So how do you determine the direction? How does the inner product determine the direction? Anyone can share your ideas. So we did it last time, right? Remember?
Questions are?
Yes, cosine. So what was the formula? You have V W, and that is size times cosine theta. So what is this theta? It's a right angle between two vectors. What does it mean? What do you mean by angle between two vectors? Because vector is nothing but a tuple of number or triple of numbers. But the theta, the angle, is geometric thing. How do you convert just the triple or pair of numbers in, which is arithmetic thing, into a geometric thing, which is an angle? So I'm showing you how to dig up the idea, right? If you just accept that it's an angle of vector, sometimes, and at some moment, you feel something is empty. The idea is empty there because, there's a gap between just the tuple of number as a definition of vector and the angle, because what's the relation here? So that's why I introduced the arrow. That's why I introduced the position vector, because position vector allows you to draw the arrow, and with an arrow, which is the geometric object which you can draw in a plane or 3-dimensional space, you can now measure the angle. You can not only measure the angle, you can see the angle as a geometric object, and that angle came from the arithmetic definition of vectors. So, yeah, once you have this, now what? We'll have to explain more. Well, this is not definition, by the way. This is the formula. Okay, so definition is here, and this is the theorem. It's more like a theorem. And how does this determines the direction, determines the directions?
question.
Yes.
So actually, inner product of two vectors is a kind of like sum of two vectors. Does it works in this way? Kind of.
Yeah, it's a sum of the multiple of entries here. Yes. But
So
sum of vector is different.
different, yeah.
Yes. Because we have how to add two vectors, and this is another vector.
Can we visualize the inner product of two vectors or not?
So it means it's the same thing as how to visualize number,
Okay.
right?
Because I said like maybe like to explain this by saying that by knowing the angle between two vectors, we can calculate the inner product, or in opposite way, if we know the inner product and two vectors, we can calculate the angle between them.
Mm-hmm.
For example, if two vectors are perpendicular to each other,
Mm-hmm.
we'll get like zero.
Yes, yes.
And this.
But perpendicular actually follows from the definition of inner product. So look at this cosine theta formula. So it's a very good point that it seems like the notion of inner product and the notion of angle are interchangeable. If you know the angle, you can get the inner product. You get the inner product, you get the angle. So it's like a circular logic. But it's really not, because if you see the cosine theta, so circular logic is the wrong logic. So if you get into the circular, then you have to think differently. So let's think about the cosine theta, where the theta actually comes from. So if you take the sizes of the two vectors to the left-hand side, what you get is inner product divided by the sizes, multiple of sizes of two vectors, right? So how do you get the inner product? This is the inner product, okay? So how do you get the sizes? Where the sizes, how does the sizes defined? So it's defined by the inner product. So everything on the right-hand side is inner product. So cosine theta, so this is a theorem, not the definition. So the theorem says the angle is same, cosine angle is the same as something that you compute by inner product. So inner product determines the angle between two vectors, but if you want to determine the angle or direction of single vector, you can't do it. You have to borrow some other vectors to describe the angle. So that angle must be relativistic angle according to that vector you borrowed somewhere else. So if you have a vector here, just random vector, you can't tell anything about the angle. You need a reference vector. Let's say V1 and V2. That's what we did last time, right? Think about what we did before. And if you follow that way, then you know what it means. So you can find the angle between V and V1. You can find the angle between V and V2. If you have two angles, so one angle is not enough, because if you have, one vector is not enough to find the exact direction, because if you have only one, let's say V1, you get a cosine theta, but this theta could be here or it could be here. So you don't really, you can't tell which direction this vector V is pointing relatively to this given vector V1. So you need another vector to determine, fully identify the direction of V. So then it's either this angle or that angle. There's no way you can get the same cosine for these two angles, so you can get the exactly one direction here. So now I said you can take any two vectors which are not parallel direction. If you're parallel, it's really not getting any useful information. But as long as it's not parallel, anything can do that to find out the direction. But usually it's better to work with the two vectors, V1, V2, which are perpendicular to each other, because once you have perpendicular vector, you can imagine that these two vectors are parallel to, let's say, x coordinate and y coordinate. So what you do in the coordinate plane is to identify the direction, right? So easy way to find out the direction once you have a perpendicular direction. So you can read a book, How to Find the Two Perpendicular Direction, once you have one vector, and you find out that it doesn't really matter whether you take 1, 0, 0, 1, which is the standard basis, or any vector which are perpendicular works the same way, because there's no absolute reference of vectors. So that's something you can put on. If you think more deeply, you can get it. So it's an irony that if you think more and more, it's not that you have something, it's not more to say. If you think more and more, you have more succinct way or more concise way of putting things in a clear explanation. So if you have something a lot to say to explain something, you have to think again whether I understand that thing deeply or not. So basically, what this is not going to be the actual question in our midterm, but this is somewhat gives you what the midterm question will be like, and whenever you study on your own with the book or by rewatching the video of a lecture, think about these kind of questions on your own, and then probably you get a good grade. Not only good grade, I think you get the better understanding of the material than anywhere else. So any questions about these questions and general ideas?
Yes.
You have a question?
So how we would answer this question?
How you answer this question?
Yeah, how we should answer actually, because
Okay.
we understand the formula,
Yes.
but how we need to explain this
So
to show that we understand it. Also,
if you understand the formula,
yes,
you can explain it.
we just need to write it like product of the length and run, I don't know, something like this.
Yeah, there's something that you have to start from. That has to be the definition and has to be just formula. It depends on your memorization, and there's something you have to explain. Let's say, for example, size is something you have to define it, but also you can explain it by Pythagorean identity, and also. Yeah, you can use the theorem, but it's not. I'm not talking that you have to copy down the formula and theorems. If you want to, there is something you have to explain, and if you cannot explain something, then you have to you have to think again whether I'm just memorizing the fact or I really understand the matter. So think about you explain this thing to your nephew, which is elementary school kids. Do they want the formula? And even if you show the formula, they wouldn't understand. So you have to explain the idea, right? How would you explain the idea to them? Right? So think about that way. So every mathematical concept are based on common sense. For example, arrow, everyone can understand the arrow, right? Everyone can understand how long is that arrow, right? Of course, you need some kind of theorem, Pythagorean theorem, to measure the size, but the notion of size itself is something you can, understand intuitively, right? And how you take the direction. How do you think about the direction? So there is a famous saying, I forgot his name, mathematician, that mathematics is not a subject that makes something complicated. It's a subject that's making complicated thing into simpler thing. So it's not exactly the same quote, but here is the exact explanation of what it means. So look at the direction. The notion of direction is so clear. Everyone knows what the direction means, right? But if you want to explain the direction, it gets complicated, right? What is direction? How do you explain the direction? And mathematics explain the direction in terms of inner product, or in terms of angle in some sense. And that gets to inner product when you have to explain how to measure the angle, and that's the inner product. So you see, if you think about, if you followed my thoughts this far, then you will agree that the angle, the notion of angle itself, is the inner product. It's not that angle exists first. It's actually the inner product existed first, and then the angle notion comes later because of the inner product. Because the only way you can measure the angle is the inner product, right? So if you understand this far, I mean, you get the whole new idea of looking at the things differently, because it gets interesting, and that's where the geometry gets interesting. Any other questions? So some of us, I know, I mean, I can guess some of us are thinking, maybe some of us will think, okay, so how this will help get a good grade in midterm or final. Okay, so it's not about getting a good grade or getting a good score. I want to enjoy of thinking, enjoy how to think. So if you do enjoy thinking of this kind of thing, then you will have lots to say when in the midterm and final, and that will eventually get the good grade. But if you're just seeking how to get the good grade and how to answer the right question, answer in the right answer, so then probably, I think it's already 2 weeks passed, so you can't switch the section, so it's too late. So I probably have to mention this before, but you should probably have to take another section if you just want the method of finding the right answer in every questions. So, all right. So if you don't have a question, let me move to our content today. So today we're going to talk about the matrix. So there's 3 questions. What is a matrix? And why do we need a matrix? And third question is, how do we use a matrix? So I'm going to point out 3 things, and you see there are 3 questions starting with the 3 different words: what, why, and how. And these are the words that you have to always keep in mind whenever you learn any new subject. When you make a question, you have to start with these 3 words, either one of these 3 words. So what is the matrix? A matrix is nothing but a 2-dimensional array of numbers. So when I say 2-dimensional, this is not about the vector. It's just that it has a row and column. And in linear algebra and any other places, like in engineering mathematics, you've probably seen that the matrix with entry of not a number, but functions or something that you can multiply and add with. So, but in our multivariable calculus, we don't consider that kind of matrix. So I will always assume that entry of a matrix is always a number. So for example, let me give this matrix. So all the entries are +1 or -1, and there is a pattern. So what's the pattern here? When is the matrix, element of matrix, become 1 or -1? So we can identify each entry of matrix by its row and column. So usually, so there is a bit difference between the Python way of writing the index of row and column and the usual mathematical way of writing the index. So in mathematics, we put the index in 1, 2, 3. So this is column 1, column 2, column 3, and this is row 1, 2, 3. So this is row and column. So if I want the ith column, j's row, I write I, comma j's entry. Okay. So, so if you're confused about which comes first, row or column, then in Korean, row matrix is haengyeol. So haeng means row and yeol means column. So you just remember the name of the matrix, haengyeol. So always the index of row comes first. And it also applies to when you take the multiplication of matrix, which we're gonna talk about this shortly. So in this case, it's either -1 or 1. So you can always represent the 1 or -1 as a power of -1. So can you express the exponent which gives the entry of A for ith row and j's column? What's the formula? What should be the formula here? So when does it become 1? So it's 1 when the row is 1 and column is 1. It's 1 when the row is 1 and column is 3. What's the pattern here?
It's the sum of row and
Yes.
column.
Is even. Yes. So it's even, then -1 to the power of even is 1. So I can just put I plus j here, right? So let me show you how to define a matrix in a Python code. So we're going to use the NumPy package. Import NumPy as NP. So there are many ways to define a matrix. So first of all, it's two-dimensional array. So you have to write as a array of array. So list of list, nested list. So NumPy has a class called array, and it is used to define a matrix-like def data. And if I just simply want to define entry-wise, then I can make a list of rows here, -1, 1, -1, and always separate by comma here, 1, -1, 1. And then this will be my A. So if I want to print out to see what the content of A is, you can use print. Yeah. And there another way. Let's write the same matrix with a coding, because I have a pattern of IJS entry. So, and also I have the size of a matrix. It's 3 by 3. So by the way, whenever you have a matrix, it has definite number of rows, definite number of columns. So you take the number of row and number of column, the pair of these numbers are called size. And we say it's 3 by 3. And when you want to define a 3 by 3 matrix, then it's an empty matrix of 3 by 3, and there's nothing in here. You can also use zeros, 3 by 3. It's the same thing, but it's empty gives the empty matrix. Zeros, sorry, still have to make a list here. Zeros give the matrix of 0 entries. So it's slightly different, but if you just want to initialize a new matrix with a certain size, you can use either one. But you have to be careful that if you initialize your matrix data with an empty function, then you have to assign value for every entry. So for I in range of 3 and for j in the range of 3. So now I and j run through 0 to 2. So there are 3 indices. And in Python, if you want to look what the entries are, the index always runs through from 0 to the number. So Aij is the ith row and jth column entry, and I want to set it to be minus 1 to the power of I plus j. Sorry, this one is bracket. And let's print it out. Oh, sorry, so it's power. Yes. Okay. So we're gonna make lots of use of this Python code in matrix. So let's see more. So matrix has an operation, matrix addition and scalar multiplication and the matrix multiplication. So let's start from the matrix addition here. So define the first, if A and B are matrices of the same size, and let's say the ij's entry of A is aij, and B has ij's entry as bij, then A plus B is also a matrix of the same size where each ij's entry is aij plus bij. So basically, you just add entry-wise, okay, same as the vector addition. Okay. Well, let's, if you want an example, some people never seen the matrix before, so I want to be clear. So 1, 0, 0, 1 plus minus 1, 1, 0. So what is it? So it's 2 by 2 matrix. You can only add the matrices of the same size. So this one has same 2 by 2 size. So you can add them together. So it's going to be 2 by 2 matrix again. So you add entry-wise, 1 minus 1 equals to 0, 0 plus 1 equals 1, 0 plus 1 equals to 1, and 1 plus 0 equals to 1. Okay. So and then there is another operation for any real number and any matrix A whose ij's entry is aij. The matrix K times A is a matrix whose entry, ij's entry is kij. Or let me write this again. Then K times A is a matrix such that ij's entry is the k times of original ij's entry. So here's an example. So let's say I have 2 times of 1 minus 1. So here, this is another matrix, 2 by 1 matrix. So it's going to be same 2 by 1 matrix, but the entries are multiple 2 of every entry here. So you don't multiply these 2 in one of these. You have to multiply to every entry, just like vectors. So when you take k times v, you don't take k into one of the entry, you take k to every entry and multiply them. So it's 2 minus 2. So once you have this addition and multiplication, it's very similar to the vector addition and vector scalar multiplication. So the matrix is vector. So you have to think about what I mean by this. But because we only mentioned the vector as two-dimensional vector and three-dimensional vector, I never mentioned about the vector itself. And if you think about or search about the definition of vector as an abstract object, then it is something that has vector addition, like a matrix addition, like here, and the scalar multiplication. As long as it has two properties, and also it has to be contain zero vector, but as long as these two operations are possible, then every object can be called as a vector. So I'm not going to go deeper into this, but just keep this in mind, the matrix is a vector. So that's why we can use the same NumPy array for vector and also matrix in principle. All right, so these are straightforward. Well, not that different from the vector addition and multiplication. Let's take matrix multiplication. So this is very important part. So let A be m by n matrix. So I'm not going to write the sentence. So here, so B is n by L matrix. Then A times B is a m is actually is the m by L matrix whose I, j's entries are. So I denote the multiple of A matrix and B matrix as A times B, A dot B, and ij's entry is given by AI1 B1J plus AI2 B2J, and so on. AIN BNJ. So here ij are run through 1 to n, m, and 1 to l. But this middle index, so it's the index of column for A, it's the index of row for B, are running always from 1 to n. So that's why we need to have the common number here. So that has to be the same. So you can take a multiplication of two matrices only when the first matrix has the same number of columns as the number of rows on the second matrix. So this is something that you, from now, don't have to remember here. So you have to understand what it means. I mean, the formula. So here's the example. Let's say I have A equals to 1 to 1200 and 2000, 300, 3000, and 1500, 2500, 2800. I'm going to explain the meaning later. Let's just pretend this is just the number I randomly put here. And this B is now 20, 23, 43. So this is an example in the book. So if you want to read meaning in Korean, you can read the book by yourself. And now A is 3 by 3 matrix. B is also 3 by 3 matrix. And you can multiply, since A has the same number of columns as the number of rows in the B, I can multiply A times B. And guess what the size of A times B is? It's going to be the 3 by 3 matrix, right? So again, the name of matrix in Korean is 행렬. So 행렬, so you have to just remember 행렬. So the middle one is disappearing, canceled out. So 3 by 3 here, the big one. I'm not going to write everything. So let's divide it into 3 parts. So maybe bigger one here, because I want to carry out the, so I only want to find out, let's say, compute the first row, first column entry of A times B. How do I do that? So first, let's just use the definition here. It says, since I is 1 and j is 1, I take A11, which is A11 here, right? 1200. And then I take B11, okay? So B11 is 20. And then next one is A12, so first row, second column, this one, plus 2, 2000. And then B21, which is second row, first column, 15. So don't care about the numbers here, because I don't want to show you how to carry out the computation, not exactly what number is. So the next one, okay, so it has to go, oh, sorry, I forgot to put the dots here. So it goes all the way up to n, not ending at here. But we only have 3 columns, so we are end here. So 3,000, 3,000, and times B31, which is 49. So just follow the blue colors here. So in order to get the first row, first column entry, I took, so this blue one, I took the first row of the matrix A, this one, first row, and then I took the first column of the matrix B. So matrix A is something that appears in the first order, in the order of multiplication, and B is the second. So if you want to multiply 2 matrices, just remember again, hang. So you take hang, the row, and take column, row. You take column, which is yar in the second, hang. So first row, first column, first row, first column. Second row, first column, second row, first column. And third row, first column, third row, first column. Okay? You take a sequel of multiplication and then multiplication and add them together, and then you get the entries of the matrix. Okay, so this one is actually, how much is it? I think it doesn't matter, it's something here. So everything is now filled with numbers. And let's think about the meaning of the matrix multiplication. So I'm going to give the meaning of each entry of A and B. So let's say you're a fruit seller, and you sell apple, orange, and banana. Okay, and you're selling it 3 days, and 3 prices set. So the first price set, price 1 is apple is 1,200, orange is 2,000, and banana is 300, sorry. And price 2, second row is the price 2, and third row is price 3. And now let's give a meaning to these entries in B. So the column here in the matrix B is day 1, day 2, day 3. And the row here is the apple, orange, and banana. So it means that in the day 1, you sell 20 apples and 15 orange and 19 banana. And day 2, you have this much selling, that much selling, and so on. So now the question is, okay, so you get some number as the first row, first column entry of A and B. What does this mean? What does this mean? So this means it's a number. What does this number mean? What do you think? So you multiply 1,200 with 20, 2,000 with 15, and 3,000 with 19. What do you get?
Total cost of fruits sold at
Yeah, total revenue after you're selling these fruits in the price set, right? So if you took the price set, price 1, in first day, then since you sold 20 apples in 1200, your revenue for selling apple is 2400, and then same for orange and so on, that banana, that's the total revenue selling your fruits, right? And so let's give a meaning here. So what each column means. So each column still means that it's the day. So whenever you have the column I, it's about the day I, right? Day 2 and day 3. And how about the row? So it's the same meaning as the row of A. It's a price 1 and price 2 and price 3. So here, if I have these meanings of entries, then A times B, the IJ's entry is the total revenue on day what? I or J? I is the row and J is the column.
J.
Yeah, so always confusing, especially when you're coding into the program. So let's be careful about that. So it's the total revenue on day J. It's not that only with price. So it's not just the price of one fruit, it's a price set of fruits. If you sell the fruits in the price set I on day J, then the amount of total revenue that you got is the I and J's entry of this matrix. So if you have an experience of dealing with Excel, then what Excel does is basically that. If you have lots of data, the practical data, and sometimes the matrix is very large and it's hard to do on your hand. So the Excel does the computation really quickly. So let's try to do computation with our computer. So we have A and B. So here, since the data is given manually, so I have to put it manually too. So 1200 and 2000 and 3000, and then let's see, 1500 and 2500, 3800. It really doesn't matter what number here is because it's not real data. So 1000 and 2200, 3500, and that's A. And let's think about B again, numpy array, and 20, 23, 43, and let's see, 15, 38, 31, and 49, 32, 30. So if you want to multiply these two matrices, you can use A times B. So it's not times here, so it's, how do I say it, at, the symbol at in your mail address. So that's the matrix multiplication symbol for numpy array. And if you want to print the result, then you put the print. And this is the result. So the entries of A times B is this much. So you can guess how much money you get on each day if you sell the fruits in certain price set. So that's what the meaning of the matrix multiplication. And in general, these are the reason why the matrix are important in practical use. But we're going to investigate deeper meaning of matrix multiplication when we're dealing with the chain rule of multivariable function. So, but you have to get used to the meaning of matrix with these practical issues here. And one thing that I want to emphasize is that when you take the matrix multiplication, it's not the same as the multiplication of numbers. So A times B is not B times A in general. So that's that's the most important thing that you have to remember for the matrix. So first of all, even if you can take a multiple of A times B, sometimes you cannot take B times A. For example, if I take A as 1, 2, 1 by 2 matrix, and B as 0, 1, 1, 0, it's possible to take the matrix multiplication because it's 1 times 2 and this is 2 times 2. 2 cancels out, so these are same thing. So the result is 1 by 2 matrix. But suppose you switch the order of multiplication, 0, 1, 1, 0 times 1, 2. So it's 2 times 2 and 1 times 2. You cannot take the multiplication between these two matrices in this order. So it's not possible. The left one exists, but the right one is not exist. And sometimes, even if you can take the matrix multiplication in either direction, either order, but the result is completely different matrix. Let's say you have these two matrices. So what's the result? What's the size of matrix multiplication on the left? What's the size of matrix multiplication? So this one is 1 by 2, this one is 2 by 1. So 1 by 1. So there's no but first row to take on the first matrix. And on the second matrix, you have only one column to take. So it's a 1 by 1 matrix. There's no other option. So it's 1 by 1 here. How about this? What's the size of matrix? So here you have 2 rows to take, 2 columns to take. So the result will be the matrix who has 2 rows and 2 columns, right? So remember the name again, 행렬. So the 행 is the first matrix, 열 is the second matrix. So row, column. So we have 2 rows to take, 2 columns to take. So that means 2 by 2 matrix. So again, this is 2 by 1 matrix, 1 by 2 matrix. The middle one disappears, so it's a 2 by 2 matrix. Just take the number of rows on the first matrix, number of columns on the second matrix. So it's 2 by 2. Size are different. They're different matrix. So even if they both exist, they may not be the same matrix at all. And let's say this case we have 2 matrix, 1, minus 1, 0, 0, and let's switch the order, 1, 0, 0, minus 1, and 0, 1, 1, 0. So what's the sizes of the 2 matrices? What's the size of the left matrix? 2 times 2, 2 by 2. So we write it as 2 times 2, but we say it in 2 by 2. So how about the size of 2 by this right matrix? That's 2 by 2. The same size. And are they the same matrix? Let's try to compute. So what's the left-hand side? So start from the 1, 1 matrix, 1, 1 entry. So 1, 1 means that I take row 1 and column 1. So what's the number? If I to multiply entry-wise and then add them together, what's it? What's that? 1, 1 here. 0, okay. So how about 1, 2? Minus 1? Yes. How about 2, 1? 1 and 0. Okay. So how about on the right-hand side? We have 1, 1, which is 0. Okay. So 1, 2, 1, and 2, 1, minus 1, and 2, 2 equals to 0. Are they same? No, they're not same. So even if you have the same size, the entry may not be the same. So just don't assume that AB is equals to BA. It just doesn't, it's not true. So you have to be careful about the order. And if you understand the meaning of matrix in terms of a differential, then you will understand why the matrix multiplication has to be dependent on the order. So yeah, I don't want to spoil it now, and I don't want to confuse it now. So okay, so let's think about the next stuff. So I want to talk about the determinant. So the determinant of 2 by 2 matrix and 3 by 3 matrix is, so there are two cases. So determinant is a number that can be defined on any square matrix, which means that if the matrix has the same number of rows and columns, then you can always define the determinant as a number. But I will only talk about the determinant of 2 by 2 and 3 by 3. So I will denote the determinant of 2 by 2 matrix as this way: A11, A12, A21, A22. So this is the matrix A with the entry A11, A22. And it's defined as A11, A22 minus A12, A21. And also, this is something that you shouldn't just memorize. Just think about picture. So here, A11, A22 are on the diagonal. So diagonal is not y equals to x direction. So in the matrix, what I mean by diagonal is the direction where the index increases. So index is increasing in this order, from left to right or top to bottom. So this is the positive diagonal. Okay? So it's called just a diagonal. And where does A1 to A21 lies in? So it's on the off diagonal, the opposite of diagonal. So this is minus. So we have a minus sign here. Just think about this cross. Okay, when you think about the determinant or try to compute the determinant, don't try to remember the formula. Just think about this picture. And 3 by 3, it's a bit more complicated also, but it's very easy to remember. Let me write down the entry first and then give you the how to understand this. So 2, 2, B, 2, 3, B1, 3, B3, 2, B3, 3. So there are going to be 6 terms in the determinant. There are 3 positive terms and 3 negative terms. So positive terms are B11, B22, B33 plus B12, B23, B31 plus B13, B21, B32. And the negative terms are minus B13, B22, B31 minus B2, B1, let's start from B1. B11, B23, B32 minus B12, B21, B33. Okay, so there are 6 terms, and only differ by, well, it's everything is different, but there are 3 terms with the positive sign, 3 terms with negative sign. The how to remember them is the following. So first, think about the diagonal direction. So these 3, so we want to combine just 3 terms with different row and different column. I don't want to take 2 entries in the same row nor same column. So only way I can do it is taking a direction. So in the diagonal direction, this is one way I can take it. So B11, B22, B33 are none of 2 of them is in the same row or column. So that's a positive. So that's a positive direction. And there are another ways to find 3 entries which are not in the same row nor column. This is this way. B1, 2, and 3. So I'm going to go over this way to get this. So still they are in the same direction, so it's going to be positive. And another way of this is this way. B1, 3, and then going back all the way to B2, 1, B3, 2. So none of them are in the same column or same row. So these are the plus ones. And how about the minus ones? They're on the off diagonal, the opposite direction of plus direction. So we have this one, which is, well, opposite direction, the perpendicular direction. And that's this one, right? And how about this one? So this one is also off diagonal direction. So right here. And the last one is this one. This one. So this one is right here. So remember this picture, like a net. So in two directions, you take, you pair three pull-up entries in different row and columns, and then you have two directions of making a group of three entries together. And if you get the positive diagonal direction, it's positive. Off diagonal, it's negative. Now, why do we do this? First of all, I want to mention about the vector thing. So there are many, so determinant is very important in the linear algebra, and you will learn more when you go to linear algebra class. But I want to mention in the vector point of view why the determinant is useful. All right, so let's say first, let V and W be two-dimensional vectors where V is V1, V2, and W is W1 and W2. Then the determinant of V1, V2, so don't put the comma here. So be careful that we don't really put the comma when you write the matrix. Although in the Python, we have to put the comma to distinguish two numbers. But in the mathematical notation, we don't put the comma. W1, W2. And this is a number, so I can take the absolute value. And this is the area of the parallelogram bounded by V1 and V2. What is parallelogram? It's a foregone where the pair of side is parallel. So we have V1 and arrow of V1, arrow of V2. Let's say two arrows have the same starting point. Then I can extend from V1 to V2 to make a parallelogram. So there is an area. The area is equals to the absolute value of determinant, whose entries consists of the entries of the two vectors. So usually we don't put the nested matrix. So for example, this V1, V2, for W1, W2s are entries, but if I have to be a little bit naive or not that rigorous, then I can combine these two into another entries of another matrix. So this sometimes I can write that as the determinant of vector V and W, assuming that V and W are 2x1 matrices. So let me distinguish that here. So this is not a rigorous way of writing it, but sometimes it's very useful to think this way, especially when you take a matrix multiplication. Anyway, so let's prove this. So I'm going to take a direction as an angle, and our standard basis, the reference vector, is standard basis 1, 0, and 0, 1. So V is going to be, let's say, size of V. So let's say R1 cosine zeta 1 and sine zeta 2. So once you find out the length, so R1 is the length or size of the vector V, and the theta 1 is the angle between V and E1, which is the x-axis. So this is E1 vector, this is E2 vector, this is 1, 0, and E2 is 0, 1, and I'm assuming V is pointing this way with the angle theta, and the length is R1, if I put it in arrow. Then also put W as R2 with cosine zeta 2 in this case, sine zeta 2. So W is right here. So the size of the arrow is R2 now, and angle is zeta 2. What I want is an area of a parallelogram. So I need to draw the parallelogram like this. And I want this arrow, the area. So if I have the area, angle in between V and W, let's say that's theta. So theta is V1 minus V2, or other way around. And maybe since I mentioned that theta 2 seems bigger than theta 1, let's put it theta 2 minus theta 1. Then the area of parallelogram is equals to R1, R2 times sine theta, right? I think it's clear from what you learned in high school, right? So let's try to get the, let's see whether it's actually the absolute value of determinant here. So determinant of R1 cosine zeta 1, R1 sine zeta 1, R2 cosine zeta 2, R2 sine zeta 2. So remember the cross here? R1, R2. Let me go back here. R1, R2 cosine zeta 1, sine zeta 2 minus R1, R2, so it's off diagonal in this case. Cosine zeta 2, sine zeta 1. Remember the sine formula? What is it? R1, R2 is the common factor. And if you want to combine this into one sine or cosine, what is it? Sine or cosine? Sine? And sine of what? Yes, zeta 2 minus zeta 1. Okay? So that's sine theta. Okay? Oh, by the way, so why do I have to absolute value in our proposition? Because in this case, in this picture, I assume that W has a bigger angle than V, but I don't really have that condition. So V might have bigger angle than W. In that case, theta is actually negative. That gives the sine theta as a negative value. So in that case, I have to put the absolute value to mention about the area. So that's why I have to get the absolute value of the determinant. In that case, determinant will also become negative value. So that's why I put the absolute value. And that's just the one part of proposition. So second part is about three-dimensional vector. So V, so now it doesn't work. So now let's say V is three-dimensional vector, V1, V2, V3, and W is W1, W2, W3. Then I have to define the cross product before I move on, but let's say, let us define V cross W. So this is the new definition of the new notation as the three-dimensional vector defined by, so this three-dimensional vector is actually defined by the determinant of 3 by 3 matrix. Now I'm going to, so I can write down the formula of the coordinates of this three-dimensional vector, but it's not going to help at all to remember the formula. So I'm going to give you way how you can remember the formula. So this is same as determinant of 3 by 3 matrix as if it has a coordinate entries of vector ijk and v1, v2, v3, and w1, w2, w3. And here, I is 1, 0, 0, three-dimensional vector. J is also three-dimensional vector. And K is another three-dimensional vector, 0, 0, 1. So what I mean by this is I'm simply writing out the formula of this three-dimensional vector, but the formula is the exactly same as if I put in determinant formula. So when you put the determinant of 3 by 3 matrix, consider for now, just ignore what I said about the matrix definition, that the entry must be number. Consider ijk just the number here. So then the plus ones are one that I can get from this direction. So it has, so this one, so V times W has I times what? V2 W3 and J times V3 times W1 and K times what? V1 W2. And then get the off diagonal. We have K first, V2 W1 minus J V1 W3 and minus I V3 W2. And then let's combine each of terms, I, J, K. So I has a coefficient V2 W3 minus V3 W2, and J has V3 W1 minus V1 W3, and K has V1 W2 minus V2 W1, right? And then now retrieve the meaning of IJK. They are three-dimensional vector, and when you have scalar multiply to that vector, it's still three-dimensional vector. So you have addition of three-dimensional vectors. So the first one is multiplying this number to 1, 0, 0, 0, and 1, 0, 0. So second and third entries are 0. Only the first one is this one. And look at the second one. It has multiple of this number to 0, 1, 0. So no other entries are changed, but the second one, so this one is still the same. And the second one is V3 W1 minus V1 W3. And the last one, V1 W2 minus V2 W1. So these are three-dimensional vector, which is definition of V times W, and it's called the cross product of V and W. Okay. So, well, I haven't started the second proposition, so because I have to define what this means. So let's take this cross product and take the size of the cross product. So this size of this vector is the area of parallelogram bounded by V and W. So that's the proposition. So what do you mean by parallelogram of two three-dimensional vectors? How do I get the parallelogram? If it's a two-dimensional vector, it's clear that it's a parallelogram lying on the plane, but we are on the three-dimensional space. What parallelogram? It's a two-dimensional shape, right? What kind of two-dimensional shape are we talking about as a parallelogram bounded by two three-dimensional vectors?
As you said earlier, find the common plane.
Yes, same as, but when you define the angle, we find the common, we find the plane that V and lies on. So this could be a slanted or somewhere else aside from the origin, but you can always find a plane. And on that plane, you can do the same thing as we did on the plane case. So this is the parallelogram. Okay? So we are talking about the area of this parallelogram on the plane containing V and W, or parallel to the V and W simultaneously. Anyway, so you see what it means? We have a geometric object, the geometric invariant, which is called area, given by the cross product of vectors, and this cross product are defined by determinant. And also, even though we didn't define it as a cross product, but in the two-dimensional case, we can also talk about area in relationship with the determinant. So you might wonder why we're talking about this thing. I mean, it's kind of interesting to see for some of us to how to relate the determinant, which is purely arithmetic, to something geometric. But we need this, really need this, when we talk about integral. When we talk about integration, so far we only talk about in your high school about the single variable calculus, single variable function, but we're going to talk about the integral of a multivariable function, and in that case we need a surface or volume. We want to take integration over the surface or volume. But then, how do I get the surface? How do I get the volume of area of a surface or volume of a region, which is round thing? The only thing we can get the area accurately of is the rectangle or parallelogram. So what we're going to do is approximate the area of a surface or the volume of a region with the area of a parallelogram or the volume of parallel pipe. So here's another one, third proposition. So let VWU be three-dimensional vector, and V times W inner product U, and let's take the absolute value again because we're going to talk about the volume, is the volume of the parallel pipe bounded by three vectors, V, W, and U. Again, well, what is parallel pipe? Let me draw the picture here. So here I have a base, V and W, and parallel pipe is something that you can draw something like this. So it's is it? So I think you have to move this way. And I think this is wrong. So this one has to go in the same area, same way, this way. So it's a kind of a cube, but it's a cube that someone pushed over, and then it's now tilted in some direction. So as I said again, this is very important when we are dealing with the integration and on the surface or the volume. Okay, so let me show you one example how to compute the cross product and inner product. So NumPy doesn't have an inner product or cross product. I mean, it has an inner product, but cross product is not in the NumPy package. So you have to import the NumPy linear algebra package inside of NumPy package. And I'm going to rename it as LA. So let's say V is array 1 to 111, and W MPy array as 1 2 3. Okay, so by the way, when you take the cross product, it only works with the three-dimensional vectors. So the cross product has a name cross, and you will get the answer of cross product of two vectors, 111 and 1 2 3. And if you want to take dot product, so then you can use dot. Oh, sorry, I used NP cross. Yeah, I don't. Yeah, LA is actually for determinant. Sorry, we don't need to import this. I didn't use LA package here. Okay, so cross and dots are in the NumPy package. So here is the cross product and here is the dot product. And well, let's try one more thing and then call it here. So I'm going to, let's say, compute the determinant. I'm just randomly write the entries here. And now I need to use the LA package for determinant. So let's print out the determinant. So determinant is in LA. So here I can see that the determinant of A is -6 for this 3 by 3 matrix. And you can actually compute the determinant for any n by n matrix, but we don't need n by n matrix for n bigger than 3. So we can only look at the definitions again if you need to compute by hand. So by the way, I'm not going to ask, let me be clear, I'm not going to ask a question like, find the determinant of the 3 by 3 matrix. Rather, I want to ask explain how the explain the definition of the 3 by 3 determinant of 3 by 3 matrix, something like that. Okay? Because you can easily get your hands on the Python coding to get the determinant. Why do you bother writing down the computation by hand? Of course, it somehow helps you remember the definition of determinant, but if you just memorize things, you will forget. 100% you will forget. So I don't want you to spend time like that. All right, so if you have any questions, let me know after class. We'll see you on Wednesday.